Namaste, and welcome back to JEE Chemistry with Typical Monk. This is Class 18, the P block, Groups 13 and 14. Group 13 opens with boron, an element so starved of electrons that it invents a whole new kind of bond. Group 14 opens with carbon, an element so generous with bonds that it builds all of life. Between them lies a chapter of beautiful exceptions, electron-deficient bridges, tight-bonded halides, and silicate frameworks that stretch from sand to gemstone, one idea at a time. Here is what you will learn today. First, Group 13, its strengths, anomalous boron, and the inert-pair effect. Second, boron's compounds, borax, boric acid, diborane, and the trihalides. Third, Group 14, the allotropes of carbon and catenation. Fourth, carbon and silicon compounds, carbon monoxide and dioxide, silicates and silicones. And fifth, electron-deficient bonding plus the drills. One idea at a time. 4 ideas. Run this entire chapter. Look at them together first. Group 13. The boron family, boron, aluminium, and their heavier cousins, mainly the +3 state, but +1 grows more stable down the group. The inert-pair effect. Anomalous boron. Small, with a high ionization energy, and the only non-metal of its group, and it is electron-deficient. Group 14. The carbon family, carbon, silicon, and below, +4 falling to +2. Down the group, the inert pair once again. And catenation, carbon's unmatched ability to bond to itself, chain after chain. It is the very basis of organic chemistry. Now, look at the picture. Diborane, B2H6, the classic electron-deficient molecule. Diborane, B2H6. It is electron-deficient. Boron has only 3 valence electrons, too few to form normal bonds to all 6 hydrogens. The 4-terminal BH bonds, 2 on each boron, ordinary 2-center 2 electron bonds, just as you would expect. The 2 bridging BHP bonds. These are the banana bonds, 3 atoms, the 2 borons and 1 hydrogen, sharing just 2 electrons, a 3-center 2 electron bonds. And the lesson. A shortage of electrons forces boron into bridged, multi-center bonding rather than simple single bonds. Now boron's key compounds. The ribbon holds the anchors, borax, boric acid, and the trihalides. Borax, sodium tetraborate, with 10 waters of crystallization, and the borax bead test identifies metal ions by the color of the bead. Boric acid, H3BO3, a weak monobasic acid, and it acts as a Lewis acid by accepting a hydroxide ion from water, not by donating a proton of its own. Boron trihalides, boron trifluoride, boron trichloride, and so on. They are electron-deficient Lewis acids, and bad bonding makes boron trifluoride the weakest of the 3. And alums, double sulfates such as potash alum, and they are used to purify water. Let us work the G favorite, ranking the boron trihalides as Lewis acids. Boron trifluoride, boron trichloride, and boron tribromide by their strength as Lewis acids. The question, simply, which of the 3 pulls electrons most strongly onto its electron-deficient boron? The naive guess. Fluorine is the most electronegative, so boron trifluoride should pull hardest and be the strongest acid. But this is wrong. Back bonding. Fluorine's small 2p lone pair overlaps boron's empty 2p orbital very well, donating pi electron density into the boron. So, the better the back bonding, the less electron deficient the boron becomes. Fluorine back bonds best, bromine worst. The order, therefore, boron trifluoride is less than boron trichloride is less than boron tribromide. Back bonding falls down the halogens, so the acid strength rises. A classic G-trap. Now the picture at the heart of silicon chemistry, the silicate tetrahedron. The silicate unit? It is SiO4 with a 4- charge. A silicon atom at the very center of a tetrahedron of 4 oxygen atoms. Sharing corners. These tetrahedra link up by sharing oxygen corners, and from that simple move, they build chains, rings, sheets, and 4 three-dimensional frameworks. Silicones, organosilicon polymers with a backbone of alternating silicon and oxygen. They are water-repellent and heat-stable. And zeolites, three-dimensional aluminosilicates, riddled with cavities. They serve as catalysts and as molecular sieves. Now what JEE actually asks. 5 pointers. 1. The inert-pair effect. The lower oxidation state grows more stable down both groups, as in thallium +1 and lead +2. 2. Diborane is electron-deficient with 4 terminal, +2 bridging, 3 center 2 electron, BHP bonds. 3. Boric acid is a weak, monobasic Lewis acid. It accepts a hydroxide ion, and there is the borax bead test. 4. The trihalide acidity runs boron trifluoride, less than boron trichloride, less than boron tribromide, from decreasing back bonding. And 5. Catenation is strongest for carbon, and the silicates build up from the SiO4 tetrahedron. Now an assertion and reason drill. For each pair are both true, and does the reason explain the assertion? First pair. Assertion: diborane is an electron-deficient molecule. Reason: boron has fewer valence electrons than are needed for normal two-center bonds to all 6 hydrogens. Both are true, and the reason directly explains the assertion. That shortage is exactly what makes it electron-deficient. The answer is A. Second pair. Assertion: boron trifluoride is the strongest Lewis acid among the boron trihalides. Reason: fluorine is the most electronegative halogen. The reason is true, but the assertion is false. Boron trifluoride is actually the weakest because of strong back bonding. The answer is D. Third pair. Assertion: carbon shows the strongest catenation in its group. Reason: carbon is the second period element of group 14. Both are true, but its catenation is due to the strong carbon-carbon bond, not merely its position in the second period. So the reason does not explain the assertion. The answer is B. Now match each compound to its fact. Borax goes to sodium tetraborate with 10 waters. The diborane bridge goes to the 3 center 2 electron bond. The silicates unit goes to SiO4 with a 4- charge. And the strongest Lewis acid goes to boron tribromide. 4 pairs, each worth committing to memory. Now, how many of these 3 statements are correct? 1. Diborane has 2 3 center 2 electron bonds. That is correct. 2. Boron trifluoride is a stronger Lewis acid than boron tribromide. That is wrong. It is the weakest, not the strongest. 3. Boric acid is a weak monobasic acid. That is correct. So the answer 2 are correct. Statements 1 and 3. The trap is statement 2. Boron tribromide is the strongest Lewis acid, not boron trifluoride. Now the 2 mistakes that quietly cost marks. The myth: boron trifluoride is the strongest Lewis acid of the boron trihalides. The truth: it is the weakest. Fluorine backbonds strongly into the boron, satisfying its deficiency. The acidity runs boron trifluoride, less than boron trichloride, less than boron tribromide. The second myth: boric acid is a strong triprotic acid, giving 3 protons. The truth: it is a weak, monobasic Lewis acid. It accepts a hydroxide ion from water, releasing just 1 proton. Now, test yourself. Answer in your head before the reveal. That is how JEE speed is built. Here we go. Question 1. The number of bridging bonds in diborane? 2. Each a 3 center 2 electron bond. Question 2. The stronger Lewis acid, boron trifluoride or boron tribromide? Boron tribromide. Question 3. The silicate building unit, SiO4 with a 4- charge. Question 4. The element with the strongest catenation, carbon. And question 5. The basicity of boric acid, it is monobasic. Let us gather it all in one breath. Groups 13 and 14, mainly +3 and +4, but the inert pair stabilizes +1 and +2 down the group. Diborane, electron deficient, with 4 terminal and 2 bridging 3 center 2 electron bonds. boron's compounds: borax, boric acid, the Lewis acid, and the trihalides, with boron trifluoride less than boron trifluoride less than boron tribromide. Carbon, the strongest catenation, its allotropes, and carbon monoxide and dioxide. Silicon, the silicates built from the SiO4 tetrahedron, plus silicons and zeolites. Next class, the P block, group 15, the nitrogen family. Boron's hunger for electrons and carbon's genius for bonds bracket a whole chapter of exceptions. The banana bridges of diborane, the back-bonded halides, and the endless silicate frameworks of silicon. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time. You will crack G. I will see you in the next class.